Welcome to solverfy.
Well, what to do if you have a really complicated looking circuit with both resistors and capacitors in it? The thing to do is to reduce these to two very simple situations. If the capacitors start off uncharged and the switch is closed at t equals 0, those capacitors act like short circuits. So they just simply let current go through just like a wire. And you don't even have to think about what value those capacitors have. If you're looking at a long time after the switch has been closed, the capacitors act just like the little diagram shows. They act like open circuits. Once they've been charged, they do not let current pass. So usually the technique is to look at those two times and develop an expression for the current through the battery using the idea of equivalent resistance. So you're going to revise the circuit so that there's a single equivalent resistance in that circuit, both at short times and at long times. And those are probably two very different equivalent resistances. So let's get started with the first case with a very short time after the switch has been closed. I like to redraw the circuit with the shorts in there so I can get a better sense of how the resistors are connected. So the first short is the 15 microfarad, and what that will do is act just like a wire and short out the top 25 ohms. And next you come to the 75 ohms. And then on the right, the first capacitor going down, the 20 microfarad, is going to act like a wire. And then you have 50 ohms attached to that. Of course, down below we have the ammeter and the 15 ohms. Those always act like resistors. Then way on the right, the next short is the 10 microfarads, which just acts like a wire. And so that wire bypasses the top 25 ohms and links to the bottom 25 ohms. So that's what your simplified circuit would look like with the capacitor acting, all the capacitors acting just like wires that bypass things or connect things. So what I can see is that the structure way off to the right now is two resistors in parallel. And I can determine that resistance by adding the inverses and then inverting one more time. And that comes out to be a parallel resistance of 16.7 ohms. Then that is in a circuit in series with the 15 and the 75 ohms. And so I can add all those up, and then I'm done. So that gives me my full equivalent resistance of 106.7 ohms. And then with that, I am down to the simplified circuit where the voltage over the equivalent resistance gives me the current through that ammeter. Thankfully, I do not have to worry about non-ideal things, such as resistance in the battery and a non-ideal ammeter. Small details. So finally, my current, we'll call this I0, is 100 volts over 100.67 ohms using Ohm's law. And that's a little bit less than 1 amp, 0.938 amps. Okay, the next case is not so hard either. At t going to infinity, the capacitors act like open circuits. And again, we want to redraw the circuit so it's a little bit easier to analyze the resistors. Now with the 15 microfarads open, all the current will go through the 25 ohms up above, and that's connected to the 75 ohms. Nothing will go down through the middle branch with the 20 microfarads. That will effectively block current. And so the second branch, nothing will pass through the 10 microfarads. It'll go through the top 25 ohms and then through the bottom. And we'll finally loop around through the 15 ohms. And then we can see that everything inside of that loop is in series. So to get the equivalent resistance, we'll just add up all those resistors. Let's see, there are 3 25 ohms and a 75 ohm and a 15 ohm. And again, we're down to a single resistor. And so our I infinity using Ohm's law is 100 volts over 165 ohms. So it is a smaller current, which is not always true. It depends on how the capacitors and resistors are arranged. But notice the nice thing, we never really had to worry about the values of those capacitors. What those capacitors essentially do is they set up a timing so that you can more definitively talk about what's a short time after the switch is closed versus a long time. But a full-blown analysis of all the time constants and the variation in time of that current could get quite complex and involve something called differential equations. So not necessary to go through that.